All right, so here we go. Back to Einstein. All right, so I was talking about Isaac Newton, who thought of gravity as a force. All right, so this is we're going to begin the thought experiments that led Einstein to realize that gravity was really the curvature of space time around any massive object. All right, so first of all, let's say you're in space and you're in some kind of space capsule, um, and so in space, of course, there's zero gravity, um, and of course Einstein realized this, and he said, "Hey, well, wait a second. If you were to turn a rocket on, or to the rocket engine, okay, so that's what's represented down here. The rocket engine would go on, and if you were to accelerate at a rate exactly equal to the rate at which things fall on the Earth, so things fall, and they fall faster as time goes on, right? So for example, if I drop something, it falls at a rate of 9.8 meters per second faster each second. So 9.8 meters per second is the way that you describe that. That's actually what's called acceleration. All right. So acceleration is the change in the velocity. All right. At any rate, if you were to accelerate upward with the exact same value as what little g is here on Earth, well, 9.8 meters per second, and you were to close off you don't have any windows or anything like that in the space capsule, the person inside the space capsule would feel normal gravity. They could weigh themselves. They could sit in their chair. It wouldn't be floating around, and yet they're out there in space. They're traveling along, but they have to have that constant acceleration of 9.8 meters per second per second. All right, so that's all right. So in this particular case, let's say that this person has two massive objects, and they drop them at the same time, and they they're in that rocket that's accelerating upward at 9.8. I know I keep saying that value, but that's an important value. 9.8 meters per second per second. So that's the rate at which it's accelerating upward. But of course, they feel like there's a downward force, right, exactly equal to gravity. And so these two things would fall just like they would do on Earth. They'd fall at the exact same rate, right? So they could perform some physics experiments inside of this rocket ship. All right. So this is what Einstein thought in his mind is what's called the principle of equivalence. Um, if the local observations made in an accelerated frame of reference cannot be distinguished from observations in a gravity field, then there's no difference. There's no difference between being accelerated in space at a rate of 9.8 meters per second, or sitting on the Earth, right? You'd experience the exact same thing. Let's see, do they have a picture of somebody if this wasn't a rocket and they were just, sitting in their room on Earth, they would just sit there and say, I could drop stuff. It would fall at exactly the same rate of 9.8 meters per second squared. All right. So anyhow, this idea of the principle of equivalence led Einstein to his next great observation. It wasn't really an observation, because at the time of Einstein, he publishes this in 1915, and the publication gets distributed in 1916. There's no way to measure this. There's no way at all that any human is going to measure this at the time. At least not with a spacecraft or rockets. They hadn't even been invented yet. So it would take an astronomical event to prove this. All right, so here's what Einstein realized is, look, if you were to send something across the spacecraft like this, so a little BB or something like that, it takes time for it to travel across, across the width of the spacecraft, right? So as time is going on, the spacecraft is accelerating upward. So it would appear that this thing. So you think about it. If you were inside of the spacecraft, this BB or whatever it is fired straight across, and yet it would seem to fall. All right. Well, and that's the situation if you're in a spacecraft that's accelerating at 1g, right? 9.8 meters per second squared. You'd see this path inside of the spacecraft. And so with this idea of the principle of equivalence, Einstein said, hey, well, wait a second. If you weren't in a spacecraft and you were on the surface of the Earth, and something was traveling from if you're just in a big room or in a room, it doesn't even matter. He actually compared it to elevators. If you're in an elevator and you're just sitting on the ground floor in the elevator's not moving, the gravitational field would feel just like the if the elevator were in space or a spaceship that was accelerating, and since there's a deflection, right, because of the acceleration, that there should be the same deflection on Earth. Like the Earth's gravity should cause this thing to deflect, and not just with like a little BB going across, but if you took light. If you actually took a beam of light and you sent it across, like a laser beam or something, it doesn't have to be a laser beam, but if you took some light and you just aimed it across the spacecraft, of course, in space, as time was going on, the light would move. Now it doesn't deflect very much because you're not really accelerating that fast, but there would be a measurable deflection. That is, it doesn't just go straight across. It deflects slightly downward, right? And he said, hey, well, wait a second. If that happens on the spacecraft, if this idea of the principle of equivalence is true, then someone on the Earth should see the same thing. And indeed, they do. But of course, it's very slight for somebody on Earth. So there was an English astronomer. His name was he actually got knighted. His name was Sir Arthur Eddington, and Sir Arthur Eddington realized that this deflection would be strongest from the most massive object in the solar system, which was, of course, the sun, right? And so the sun would bend the light the greatest, right? And Einstein actually predicted what this angle would be, this angle of deflection. Now, we know where the stars are, right? We've been measuring the stars, even during the time of Sir Arthur Eddington in 1919, we had taken photographs of the stars. We knew right where the stars are supposed to be with respect to each other. So if you can see a star during the day, right, that's the key, right? You got to be able to see the stars during the day. The starlight that passed really close to the surface of the sun would be deflected by a certain angle that was exactly what Einstein predicted in the general theory of relativity. And that angle actually turns out to be 1.75 in units called arc seconds. So 1.75 arc seconds with something that has the same size and the same mass as the sun. So anyhow, Sir Arthur Eddington says, well, hey, there are times that you can see the stars during the day, but there has to be a solar eclipse. And so there in 1919 there was going to be a solar eclipse. I think it was remember, it's the shadow. You got to be in the shadow of the moon for that to happen. The shadow of the moon has to pass across you, and so that happened. I think it was there was some islands off the coast of Africa, off the coast of Eastern Africa, and so he took his equipment and a team of people to observe this eclipse and to measure this angle of deflection and to see if Einstein was actually right or not. And so in 1919, Arthur Eddington, makes this trip with his team and measures it, and the angle is exactly what Einstein's theory of general relativity predicted. All right. So now let me go back just a step. Isaac Newton, has his theory of gravity. That is, of course, the gravity is a force that causes the planets to orbit the way that they do. Einstein's theory of gravity and Newton's theory of gravity are actually very similar to each other. The thing that Einstein's theory does is it's just more accurate in extreme situations. I mean, we still use Newton's theory of gravity to go to other planets, to land on other planets, to send spacecraft to asteroids or comets. I mean, it does a great job of that. We don't need Einstein's theory of gravity to predict that. Where you do need it is for very fine, for a much finer description of how gravity works. All right. Once this observation was made, and Einstein's theory of general relativity was proven, this actually makes Einstein like world famous overnight. He becomes really famous. One of the results is that not only does this affect the bending of light, but it actually affects time itself. So time closer into to the center of the Earth. So let's say you have a clock right here, and then there's a clock well above the Earth. Let's say it's on an airplane or something like that that's flying around the Earth. The clock that's closer to the Earth will run slower than the clock that is up higher. And in fact, during Einstein's life, there was no way of proving this with clocks anyway. We did prove the deflection thing, and that's what made him so famous. But of course, if you make this prediction about time, that time will run slower, the closer you are inside of a gravitational field, and then you have to actually prove that, right? That's the scientific method. And of course, in the 1960s, so this is after Einstein had passed away, we took an atomic clock, a very, very accurate clock. It was in sync, perfectly in sync with a clock on a jet airplane, and we flew the jet airplane all the way around the Earth. And when it came back, we compared the clocks. Right. I mean, they're not crude clocks like this. This is very crude. But an atomic clock is extremely accurate, and the two clocks were off exactly by the amount that was predicted by the general theory of relativity. So clocks do run a little bit slower close to the surface of the Earth. All right. So, it's not much. I want you guys to understand that. It's not much at all. I mean, you would have to be, if you were on an aircraft and you flew around the Earth like your entire life, you wouldn't be, let's say you had a twin, right? The one twin was on the aircraft that flew around the Earth for their entire life, and then the other twin was on the surface of the Earth. The twin on the surface of the Earth would not have gained even a second